The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Okay, we could continue. Last time I was talking about cognition and framing the argument in part in saying that we're not like computers, even though computers are nice metaphors for various aspects of cognitive function. We could continue that today. When you get an off-the-shelf computer, you expect that its basic way of thinking is going to be, it's there. You might have to put some programs on it to teach it to do specific things, but you don't have to educate its motherboard or something of that sort. With kids, it's not clear that that's the case. That if you take an off-the-shelf baby, it's not clear that that baby is thinking the way that an adult is thinking. And that's really what I want to talk about today. Let me put up a picture that I can then return to multiple times. If this is age, and we're interested in development, what we were talking about last time is the adult state. Something about the adult state. What we want to know in studying cognitive development, or any sort of development, is what's the starting point? If you have a newborn baby, is that baby starting at 0, or does that baby come with some sort of an innate endowment that allows them, that gets them on the way towards the adult state? And then what does the transition from the kid state to the adult state look like? Does it look like some sort of gradual improvement? Does it look like some sort of step function? It might be useful to describe from the realm of vision a couple of examples just to show you what this means. If you want to know what a baby sees, if you go and we'll go over here. If you get yourself a newborn off-the-shelf baby and give them, you can't give them an eye chart to read because they can't read, so, you give them the illiterate E chart, as it's called in the trade, and, and so on. And you ask them which way the letters point. The kid doesn't tell you anything useful, right? Because the kid can't answer that question. However, conveniently enough, if you take even a newborn baby, as young as you can test them, and put them in front of a couple of screens, little peephole here, you guys can all be babies, and the experimenter, would be looking out at you through this peephole. If you put black and white bars on one screen, and you put on the other screen a gray of the same average luminance, so if this is 0 and that's 100, this is 50 all over the place. If the baby can see the bars, conveniently enough, that baby will look at the bars. If you are looking at the baby, you can figure out, you move the bars from side to side, from trial to trial, you can figure out where that baby is looking. You can figure out where the bars are based on where the baby is looking. That's known as a preferential looking method, very useful in infant research. And what you discover if you do experiments like this, studying infant visual acuity, is that babies don't start at 0. Babies don't start, newborn baby isn't blind. Newborn baby can see something. If normal adult vision is around 20/20, newborn baby vision is around 2400. It's the big E at the top of the eye chart, roughly. The progression from the infant state to the adult state is a gradual, relatively steady increase over about the first couple of years of life. Every month, you get roughly the same kind of improvement until you hit the adult level. So, not a 0 starting point. and a gradual improvement to adult levels. Now let's take a different example from the same realm. Remember, you've got two eyes. The differences in those two eyes are a depth cue, known as binocular stereopsis. Well, the cue is binocular disparity. The ability is stereoscopic depth perception. If you test a baby, so babies, it turns out, also like things that stand out in depth better than they like flat stuff. So if you show a baby bars standing out in depth, a newborn baby gives you squat. To all appearances, there is no binocular stereo vision in a newborn baby. And for about the first 3 to 5 months, nothing happens. And then over a very short period of time, I should get rid of this other step function just to not confuse matters. Over a very short period of time, performance rises to essentially the adult level, as if this was waiting for something to get wired up in the brain. When it got wired up in the brain, bingo, the kid is fine. Oh, by the way, if you are a woman person, you got there first. It turns out to be a reliable sex difference that females get binocular stereo vision a month or so before males. Does this make any difference to anything? No, but we found it years and years ago when I was a grad student, so I still remember it. So these are two of the various possibilities for a function like this, for a developmental course. And we're going to look at, we're going to talk about 3 specific realms of cognitive development in which there are classic demonstrations of children doing things differently than adults do them. And I will try to take each of those apart and to give you some idea of what's the starting point, what's the ending point, and how do we get between those. The 3, which are outlined on the handout, have to do with number, so-called childhood animism, and egocentric behavior. Let me describe each of these problems to you in turn, and then we'll take each of them apart. The classic, these are all demonstrations that originally come from the work of Jean Piaget, the great early mid-20th century developmental psychologist, who, among other things, bequeathed to us a great collection of phenomena that show striking differences between the way kids behave and the way adults behave, and that cry out for explanation. So here would be one of them. These are M&Ms, let us say. That'll do. Uh-oh, I'm running out of space here for my M&Ms. Well, people over there can't see them. Can you see that M&M? Wait a second. I'll put them down here. That'll work. There we go. Don't worry about these M&Ms. Okay. This is another one of those forced choice kind of things. So think hard about this. Are there more M&Ms here or here? How many vote up? That's good. However, if you were 3, 4, 5, maybe even 6, you'd say here. You would be perfectly happy. Yeah, you think that's good. That's nice. It makes math a little more difficult here at MIT, but we shouldn't stifle your creativity. That's good. And so the first obvious thought is, well, the kid's just not quite understanding the question. It's a languagey kind of thing. We're saying where's more, and they're saying which is longer. So that's why it's important that you use M&Ms. You say, okay, kid, which pile would you like? Kid says, I want this pile. Why do you want this pile? Well, there's more there. So, and in fact, this is why you shouldn't be born to a psychologist. because your psychologist's dad is always tricking you out of the candy by playing this game on you. It works. It's good. You teach this stuff long enough, and you think, is this really true? And then you've got yourself like a 3-year-old kid, and you mess with his brain, and yeah, it's true. This is good stuff. But so you want to know what's the question here, of course, is then what's going on. This is part of a general problem. If you take, so let's take a fat beaker. Here's a big fat beaker with this much fluid in it. Now I pour that into a narrow beaker. The water, the fluid level is higher. Is there more fluid now than there was when it was here? No. Does a little kid think there is? Yes. If you let the little kid pour it back into the big bowl now, he thinks there's less now. Take a ball of clay, roll it out into a snake. There's more clay, says the little kid. Squish it back together, now there's less. These are so-called conservation problems. We're particularly interested in the version that has to do with number. How come they think, in this case, that 5 is bigger than 6? Second problem is what's called childhood animism. The classic Piagetian version would involve something like, something exactly like his so-called 3-mountain apparatus, where he had sort of a tabletop. He's from Switzerland, so he's into the Alps, right? So it's a tabletop version of the Alps. And on the Alps are things like that's a river, and that's a hut. It's where the pie maker lives, right? So anyway, the point is that you're sitting here looking at this thing. You're like a 3-year-old or something looking at this, and Mom's over there on the other side. You can see Mom, and the question that you're asked is, can your mother see the river? And you say, yeah, sure. As if the fact that you could see the river makes you think that she can see the river. As if you couldn't take her point of view. At least Piaget thought that the problem here is that you can't quite take somebody else's point of view. My favorite anecdotal version of this is a story of a little kid out to eat with his brother at some burger place. Little kid wants more French fries, and so he does this. On the theory, presumably, if I can't see what I'm doing, you can't see what I'm doing. So most people don't do that by the time they reach adulthood, right? So there's something to explain there. That's childhood. That's not childhood animism at all. Actually, that's egocentric behavior. Sorry, I misspoke. That's the third example that we'll get to. So egocentric makes more sense. Egocentric is the inability to see things from somebody else's vantage point. So I've just described to you the problem of childhood egocentrism. Childhood animism is a tendency to declare things to be alive that you would not declare to be alive. Is the cat alive? Yeah, fine. Is the sun alive? Yes. Are the clouds alive? Yes. Little kids will assert that, and you typically will not. That's animism. Piaget understood that as a problem with mapping concepts onto a discrete set of entities out in the world, and so we'll take a look at that too. So, number, animism, egocentric behavior, those are the things that I want to talk about today. Let's start with number, and let's start by taking apart the idea of number a bit, because you and I tend to think of number as there's 5 of those things and 6 of those things. Number, the concept of number, the idea of number can be broken down into 3 different bits at least. And let's see if I can do this right. Whoop. Oh, well, they went by. How many warthogs were there? 6? Who knows? Yeah, some. Now, wait a second. Let's try this again. 9, 8, 7, some number like that. It wasn't 115, but how about this? Yeah, okay, that's good. Whoops, how about this?
3.
Whoops, how about that? How about this? This is data. If you do this task, what you find is that people are essentially perfect for 1, 2, and 3, maybe 4, and then it falls off. They start. I think the answer was 8 before, but sometimes you say 7, sometimes you say 9, and so your percent correct, being absolutely correct, will systematically fall off. And if I put 1,500 warthogs up there, you'll just not get it right at all. Similarly, if I was to measure not percent correct, but reaction time, the reaction time for 1, 2, 3, 4 would be essentially flat and then start to roughly linearly increase. That linear increase could be, for a number like 8, could either be due to some sort of counting operation or how many people... somebody who thinks they saw 8 of them, tell me how they figured that out. Yeah. A line of 5 and 2 and 1. Okay, well, that's yeah. Okay, yes. If I was doing this as a proper experiment, I would have masked it so you couldn't count like the after image or the iconic memory. So they're yep. Okay, so you were also dumping it out of iconic memory in some fashion. The answer I was fishing for is something like the 5, 2, and 1 thing, that you can count those displays, and in fact the people who got them back later might have done this too, by more typically saying, oh, there's one group of 4, there's another group of 4. This ability to handle small numbers is called subitizing. And it works for small numbers like 1, 2, 3, 4. You have some immediate appreciation of that number, of those small numbers, that's different than your appreciation of 8 or 17 or 150. Okay, that's one warthog demonstration. How about, which one has more warthogs? How many vote that there were more here? How many vote that there were more here? Yeah, okay, you got that, right? You knew. How many warthogs were there here? A lot, yeah. And how many warthogs were here? A lot, but not as many. Well, you can go back. There we go. You can count these, obviously, but you didn't count them. And you didn't subitize them. What you did was you got some sort of general impression of their numerosity, because, this is, if you go back to the perception chapter, this is another Weber's law kind of thing, or the money example from last time. You can also decide something about how many things there are there by a sort of a ratio comparison. There's more here than here. If there were 750 here and 745 here, you wouldn't know that. There has to be a critical proportional difference between the two. But given a proportional difference, that this is something like 2 to 1, like that, it doesn't matter how many things there are. You simply know that there's more here and less here. That's a sort of a crude sense of numerosity. The variety of what we typically think of when we think about numbers is counting things. And that's the third property. So here you can count them. Somebody can go and figure out exactly how many warthogs there are there. You just have to go through and use your counting ability to figure that out. You have that ability. It seems to be critically piggybacked on your ability, on linguistic ability. Recent interesting evidence for that comes from, I don't know how to pronounce it properly, but something like the Paraha tribe in the Amazon. Their number terms consist of 1, 2, and more than that. And the result is that they bomb tasks that require counting. They can do subitizing tasks. They can do numerosity tasks, but they don't do counting tasks. And they will fail, they fail versions of the M&M task, in effect. You say, which of these boxes has, do you want, they got fish in them or something like that, and one has a little label with, I think, 4 fish on the top, and another has 5 fish on the top, and as far as these guys are concerned, it's all just got lots of fish. What you see here is a task where they were, this was the experimenter's marks, and the Paraha person was asked to just copy it. So, 1, I make 1 mark, 2, I can make, that 2 marks, 3, all right. That's just a bunch, I'll make a bunch of marks. Once you got out of the subitizing range, they simply didn't do the task. I think I put these guys on this article from which I stole this picture may live on the website. I seem to remember that was one of the things that I posted there. So, what do kids have, and how does that tie into to the M&M problem? Well, turns out that little kids have, babies have this numerosity, Weber's law, comparison kind of numerosity ability. And here's an experiment done by Shu and Liz Spelke up at Harvard that illustrates that. You're a baby. You're looking at this. Okay, and every now and then the display changes. Boink. Yeah, okay, here's another bunch of dots. And another bunch of dots. And what I'm doing is the experimenter, am measuring how long you look at this. And I'm changing the shape and the distribution of these guys, but I'm not changing the number. And you are slowly getting bored. Or to be more technical about it, you're habituating. You may recall that from the learning chapter. I don't think we talked about it in the chapter. Well, we can talk about it right now. Oh, bunch of people oriented to that. And now those people are having no problem at all Zing back out again, right? That's habituation. You do it, babies do it, slugs do it, everybody does it. It's great. Useful technique, because the baby's sitting here saying, this is all kind of more or less the same, and it's just not that interesting. Whoa, wait a second, that's interesting, says the baby. And the baby says it by looking more. What happens here is that, looking time goes down, 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 down as the number on each trial stays the same. Then when you jump from 8 to 16, the baby says, hey, something's happened, I got to take a look at this. Do 16 for a while, blah, 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 blah. And what this tells you is that the baby could tell the difference between 8 and 16. The reason for changing the shape and the distribution and the density and stuff like that is to make sure that that's not what you're picking up on. And Shu and Spelke were careful about that. So what you're picking up on here is numerosity. Babies can do that, but if you go from 8 to 9, nothing happens here. In fact, if you go from 8 to 12, a 50% increase in dots, nothing happens here with, how old are these babies? 6-month-old babies. So 8 to 16, a 2-to-1 change, that babies pick up on. So, one thing we know, let me get my graph back here. Oops, graph, come back, graph. Get my graph back down here. So we know that if we're talking about number, the starting spot isn't 0 for number sense in infants. The numerosity piece, some chunk of the numerosity piece is there for starters. Perhaps more dramatically, the subitizing piece is there, and the subitizing piece is there along with what seems to be an innate mathematical ability. Little kids can add and subtract. Babies can add and subtract. This was a surprise, and this is work done by Karen Wynn, and it is worth making the historical note that she was a TA for this course once upon a time, now a professor at Yale. But in any case, she figured out that babies can add and subtract. Look, if you ask a baby what's 1 plus 1, you get much the same answer as if you ask the baby which way is the E pointing. You got to get clever about this sort of thing. And here's how Karen got clever about it. So you're looking at a screen. You're a little baby looking at a screen like this, and you see a hand come in with an object, sticking. It probably wasn't a warthog, but I had this warthog lying around as a image on my computer for some reason. Okay, so and you see a hand come in with another one. Okay, you got a pretty good idea what's going on here, right? So if I lift the screen, what do you expect to see? Oh. All right, now we can do this again. Whoop, whoop. Okay. The speed would be the same, of course. I just didn't want to keep sliding them in slowly. I'll move the screen again. And the baby will respond to this by looking longer. The baby will say, who knows what the baby will say, but the baby is apparently, in effect, saying, all right, put one thing in, there's two things in there, I guess, there's two warthogs back there. Lift it up, and now there's only one warthog, and this violates the rules of the universe, and I better look at this for a while to figure out what's going on. And you can use this technique to show that babies can do. Do I have a subtraction one here? I forget. No, that's going to. I did that already. Yeah. They'd habituate. No. It works for monkeys too. We'll talk about that in a minute. But you can do this. You can do addition. You can do subtraction. So subtraction. You have the two things here. You put down the screen. The hand comes in and pulls one out. When the screen comes up, the baby expects to see 1. If the baby sees 0 or the baby sees 2, the baby says, something weird's going on here. I need to think about this for a while. Now, if you do this with big numbers outside of the subitizing range, you don't get the result. So, you stick 15 warthogs back there, and you lift up the screen, and there's 13 warthogs, and the kid says, I don't care. Once you get above about 3 with babies, it doesn't work anymore. So what you get is evidence for subitizing being present, and some sort of addition and subtraction kind of operation for essentially as early as you want to test it. You can also get these abilities in animals. That's what this slide is intended to remind me to tell you. Animals, certainly macaque monkeys, will show numerosity effects, and they can also do this sort of Karen Wynn style math. They prefer eggplants. At least Mark Hauser's monkeys like eggplants, so that's why there are eggplants here. And you worry about doing this in the lab because maybe your lab monkeys have led this elaborately studied life and are kind of smart. So Hauser went down to this island in the Caribbean where he's got a free-ranging troop of monkeys, and then you kind of have to coax them into playing your game. So you're hanging. There's this great video that Mark has of monkeys. He's hanging out with his eggplants. And then he's starting to do this eggplant puppet show with the macaque is looking longer at the weird ones, right? And the guy put two eggplants there, and there's only one there now, man. Hope he's going to feed me some of these eggplants eventually. But in any case, monkeys can do the task. Monkeys will look longer at things that violate their expectation. However, monkeys don't count. At least they don't count the way that you and I count. And this goes for great apes. Fine. Let's go find the brightest beast other than humans that we can. There's at least one chimp who's been trained for 20 years. I misspoke when I talked about this in concourse. I said he'd been trained for 9 years and never gotten past 20. It's worse than that. He's been trained for 20 years and he's never gotten past 9 counting. He can count to 9, do pretty good stuff up to 9, but he's doing this by basically association learning. Up you go, and let's turn that on and let it come back up. You can train the monkey to realize that this sign or this graphic or something means 9 things. But this is very different from what you and I can do. It didn't take you 20 years and you got well beyond 9. Counting seems to be heavily dependent on 2 things. One is language, and the other is an act of inductive reasoning. And you can sort of see counting happening, the development of counting in a series of steps. Kids, as they are learning language, learn that that there's this kind of game about saying 1, 2, 3, 4, and so on, that parents really like to play. If you start counting, they'll give you the cookies and stuff. Good things happen. They don't have any particular clue that this maps onto anything in particular. So what you get with like 2.5-year-old kids is a 2.5-year-old kid, if you ask for 1 cookie, will give you 1 cookie. But if you ask for anything else, give me 2 cookies, give me 4 cookies, give me whatever, they'll give you some random bunch. Here, have some cookies. It's 1 and other stuff. Eventually, they learn to map the counting onto the subitizing range, and then start blowing it later. So if you have little sibs or cousins or stuff that you've hung around with, you may have seen them counting things 1, 2, 3, 4, 5, 7, 12. And they got this notion that the numbers keep going in some fashion. But once you get out of the small numbers, it's not terribly clear what's going on there. But even in this stage, you can start to see the development of something more sophisticated. 6. They may not know how many 6s. They know 6 is a lot of stuff. If you ask for 6 cookies, you'll get some arbitrary number of cookies. But if you ask a little kid, if I take a lot of cookies and I add a few, do I still have a lot of cookies? Kid says, yeah, it works. Kid says, and so all right, so we know that. Okay, now if I have 6 cookies, can you give me 6 cookies? Some random number of cookies. Okay, if I have 6 cookies and I add some more cookies, do I still have 6 cookies? No, you got a lot of cookies, but it's not the same a lotta. Right? So even when they don't really know how many cookies you've got, they have the notion that the number names are naming something specific. They don't quite get what it is, but it's something specific in a way that a term like a lot is not. Eventually, you make the breakthrough that you can count, basically. And that you can keep, and if you add 1 to each of them, you can just keep doing this forever. This is, again, I don't know how much you hang around with little kids or remember your own experience, because this is getting old enough that you might actually remember this state yourself, of asking what the biggest number in the world is. Anybody remember asking what the biggest number in the world is? Yeah, well, all right, most of you got, that's the problem with MIT students, right? They figured all this stuff out when they were like 2 instead of... So, anyway, little kids want to know what the biggest number in the world is. And so you say to the little kid, well, what do you think the biggest number in the world is? Well, it's 1,000,000. Okay, what happens if we had a million plus 1? Is there a number for that? Oh, yeah, it's 1,000,001, I guess. Well, I guess 1,000,001 is the biggest number in the world. Well, if we add 1,000,002, you can keep doing this for a while. Eventually, around the time when you get in this conversation, the kid catches on to the notion that you can always get a bigger one. And this is really leads to very boring car rides sometimes. Right? Do you want to see how high I can count? That's a kind of cute game with a 3-year-old. Oh, look, he can get all the way to 20. By the time you get 4 or 5-year-old, 1,000,001, 1,000,002, 1,000,003. Okay, we've made it to California, kids. Shut up. So what you get is you've got this you've got this basic numeric competence, or core knowledge, as Liz Spelke would call it, and then you're waiting for the development of language. When you get language, you can then get this counting piece to work. When you got the counting piece to work, you can combine it with your ability to make the inductive leap that numbers go on forever, and then you're in a position to go off to school and learn some math. So the ability, there's in a sense not an adult level of numerical competence. You guys know more about numbers than I know, I would imagine. But the ability to go off and learn that kind of math is based on this core knowledge, then waiting on language before you can make the leap to an ability to use to do 18 or whatever. So it's an example, if you like, of the synergistic combination of information from a couple of different realms. Let's switch to the problem of childhood animism. That, if you're not completely confused from my earlier misspeaking, animism is the tendency to say, is the sun alive? Yes. Are clouds alive? Yes. That seems quite different from what you and I do. One might wonder exactly how different it really is. Does it really reflect a fundamental problem with the concept alive? It's not that obvious how you map a concept like that, even as an adult. It's perhaps easier to think about in connection with dead. Mapping dead onto a discrete set of things is not that trivial. Is a rock dead? Probably not, because it was never alive, right? Is George Washington dead? That seems about right. Is he dead in the same way that something that like a cat that just recently died, that's here dead now? Is that the same? How about a dinosaur? Or the dinosaurs. Are the dinosaurs dead? Well, yes, they're dead, but they're also extinct, which is somehow kind of different. Or to use an example from driving around, now that my kids have gotten out of the counting to 1,000,000 stage, I don't know how we got on the subject of what is alive, maybe because I was thinking about this lecture. But anyway, my 10th grader asked my 3rd grader, is fire alive? Well, I don't know about the 3rd grader, but it took Dad in the front seat a surprisingly long time to figure. Well, Dad knew that the answer is no, but the principled reason why it's no took me a couple of beats to get to, because fire breathes, right? It grows, it reproduces, it can die, it can do all those good things. Turns out that in 10th grade biology they teach you that if you're going to be alive, you've got to be made of cells, and fire's not made of cells, except that then you get into 11th grade English and you read some sci-fi novel where this thing is alive, but it's just a force field in deep space or something like that. I don't know what to do about that, but concepts like alive are pretty complex stuff, and the fact that a kid doesn't map it exactly the same way you map it may not be that definitive. Does the kid have a concept at all that they can use? That's what we really want to know. What's really going on there? So maybe we ought to ask the question a little bit differently. Kid has some notion of what alive things do. So suppose we ask a kid, does a cat breathe? Yeah, cat breathes. How about a cow? Yeah, cow breathes. How about the sun? No, I don't think so. The moon? No. The clouds? No. So and you can do the same thing with babies. Not asking the babies, but talking about, can a cat have babies? Yeah, sure. Can the sun have babies? No. And you get the feeling that there's a concept there, that they're just not using the word alive the way that you and I are using it. Well, maybe all you're looking at here is the fact that they don't actually have a concept. What they have is a long list of learned instances. They all hang out at these fancy, upper middle class preschools where they get taught kitty has babies, cow has babies, and they never get taught sun has babies because the sun doesn't have babies. And so they learn all this stuff. Maybe it's not a concept. Maybe it's just a list of instances. How can we figure this out? Well, Sue Carey did an experiment where what she did was she taught kids something new. She said, see this cat? This cat has an omentum. And you have an omentum. And the cow has an omentum. Now, how about the sheep? Think it's got an omentum? Probably got an omentum. How about, and the dog? Yeah, the dog's probably got one. How about a fish? Yeah, probably. Could be. Worm? I don't know. Possibly. Rock? Nah, rock doesn't have an omentum. And how about sun? Nah, sun doesn't have an omentum. You don't have one either, it turns out. She wanted a real biological term, but she took, I think it's some weird membrane that an insect has or something like that. But the point was that it wasn't something that you would have ever learned. It's a new piece of knowledge. And if you say that things in this category, things in the category that are encompassed by cats, cows, and you, all have this, who else has it? And little kids, 3-4-year-old kids, map this in a plausible kind of a way. So it might map something like mammal, it might map something like animal. I don't remember if any of her kids mapped something like alive, in which case they would assert that a tree had it too or something. But it maps a concept that has a biological ring to it. What's the difference between the childhood use of these concepts and the adult use of these concepts? It seems to be, in this case, education. You go to school to learn the right concepts. In this sense, there is no firm adult state. I mean, my job here is to teach you a collection of facts and the right concepts in psychology. But I can teach you some of them. And I keep learning new ones, and the adult bar keeps sort of drifting there. You sort of go off to learn these sort of concepts, but you don't learn to have a concept per se. What the kid is doing, well, actually it's rather similar to what we're doing here. The kid is mustering the data that is available to him, and working with the concept as long. So what do you figure? What do you think the concept of alive is for a little kid? What do you think goes into it that causes little kids to give the wrong answer when asked by Piaget what's alive and what's not? What's the critical difference between your notion of alive that you picked up in 10th grade biology and a 4-year-old's notion of alive? Anybody? Yeah.
Something alive is something that moves, and you didn't see why it moves.
Yeah, so moving on its own seems to be an important. So cars aren't alive because you've got to make them move in some fashion. But self-produced motion seems to be an important part of the definition, and the sun and the clouds and the moon seem to scooch around in the sky, particularly if you're driving in that car, in ways that suggest that it might be alive. It gets a little more complicated because kids have also learned that trees are alive, and outside of Lord of the Rings, trees don't do much in the way of wandering around. But growing on your own is good too. And that would be part of the biological definition. But it's the self-produced motion thing that kids regard, that kids overuse in their definition, seemingly, that you don't use. You can see, if you get transcripts of little kids using language, you can get a feeling for this little scientist aspect of childhood concept, of concept formation, concept verification. So here from the what is alive literature is a kid who is asked, are rocks alive? And the answer is yes, rocks are alive, but they're only alive until you step on them, and then they die. Which is kind of reasonable, right? The kid's got presumably some experience with other things like that. This ant, the ant's alive. Step on it, it's not alive anymore. And he can actually, and this kid produces some evidence in favor of this theory, which is, if you look on a path, how big are the rocks on average? You know, you can take a walk in the woods, down a rocky kind of path. There are rocks on there. They're kind of small rocks. You look off across, at the mountains. How big are the rocks? Well, they're huge. What's going on here? Well, on a path, people are walking all the time, so the rocks die real young. And they never get to grow big. Whereas the rocks off the path, out in the mountains, they got to grow to be really big rocks. It's not a correct theory, but you can see the kid using the data he's got. Right, a certain amount of data there. If I step on it, it dies. Maybe that's what happens to rocks, and people step more here than they step there. So big rocks, little rocks, it all hangs together. I got a great theory here. Or another one: are rocks alive? Yes. Can they have babies? Yes. Are all rocks alive? No. Some rocks are dead. How can you tell if a rock is dead? Well, the dead ones just lie there. This is capturing the notion of that motion is important in little kids' definitions of the notion of aliveness. And then I don't know how many rocks he saw moving under their own power, but in any case, you can see the little scientist aspect of this. Okay, so what's the starting point here? The concepts that you're building seem to have some foundations that can be picked up very early and are probably innate. I'll just talk about two of them here. So concepts about things like aliveness. If you're going to decide that a thing is alive, you need, for starters, to know that it is a thing. So you need to have some notion of an object. And the other thing you need is some notion that objects, classes of objects, have essences. This is, I think it's on the handout somewhere as... Did I write? Yes, yes, towards the bottom of page 2, it says essence, and there's a reference to Susan Gelman's work on psychological essentialism. The notion of an essence is a property that's not visible, or at least not currently visible. It's got to be, in order to have these sort of category things, you've got to have the notion that objects continue to have properties even if you can't see that. So, for example, I won't embarrass anybody, but there are people here presently who are not moving, who are not, to all appearances, growing. I can't tell from this distance whether they're made of cells, and they don't appear to be having babies or anything like that. Nevertheless, I assume that they are alive. That's part of their essence. That this aliveness is something that I attribute to that object without being able to see it. Now, what's the evidence that little kids have that? Well, I'll tell you that, and then we'll go on, have a break, and then we'll go on to the problem of egocentric behavior. So, I need a tube. This is. Let's start with evidence that babies know something about objects. So, here's a tube. If I was doing this right, I'd show you that there's nothing in the tube. And and then I would take a stuffed animal. Here's a duck. Okay, so I would take the duck, and he's a squishy duck, so I'm going to stuff him in the tube. Okay, And then, so the baby's watching all this cool stuff happening here. This is a little baby's watching this stuff. And then I take, Nemo or whatever, my little plush Nemo, and I stuff him in the tube. Okay? You with me so far, babies? Now, I reach into the tube, and I pull out. I pull out the fish. And you, being good babies, stare at this. You say, this is weird stuff, because I saw the duck go in first. And this is not quite Liz Spelke's experiment. I realize I'm getting the methods a little screwed up, but the principle is right. I saw the duck go in, then the fish went in, and I know about objects. Objects do not interpenetrate, right? Objects are solid things, and if the fish is out here, where'd the duck go? And Spelke's done a series of experiments like this that suggest that kids know about babies, young babies, as early as you can successfully test them, so getting very close to being at the starting point, know about objects, and know a few things about those objects, notably things like that objects don't interpenetrate. They don't know everything about objects. So they don't, for instance, if you set up some fish and ducky kind of thing that violates the law of gravity, kid doesn't care. They don't seem to be particularly sensitive to gravity. Yet a 2-year-old or so in his high chair, 2-year-old in the high chair thinks gravity's great, right? Here's the hot dog. Ooh, yeah, okay, so Dad picks up the hot dog and puts it back on the plate, and the kid drops it again, because he's got to check, he's a little scientist, right? He's got to check that gravity is still, you'll get there. Mara knows about gravity, but her baby doesn't know about it yet. Her baby looks at gravity demonstrations and says, this is really boring, but her baby knows that the fish cannot go through the duck. It just would be bad news for the duck. Babies don't care about inertia either. And, things like objects in motion continue in motion unless acted on. But tell that to a baby. The baby says, "Yeah, right. Don't care about that." But I know that the fish does not go through the duck. That's this notion of objects. What about essence? Well, essence is harder to get to in early childhood. It's harder to ask the question. But by the time you get to... How old are we in this experiment? You're like 2 or 3 years old. But you're doing something like this. You take the duck and you say, see this duck? What we're going to do is we're going to do an operation on the duck. I promise it's not going to hurt the duck. But we're going to take off his skin and we're going to put raccoon skin on him. He's going to look just like a raccoon. Right? Now, is this a duck or a raccoon? And as soon as the kid can meaningfully answer the question for you, the kid will say, that's a duck. I mean, you dressed him up like a raccoon, but he's a duck. Inside, he's got duck essence. He doesn't say anything about duck essence, but he knows that there's a core of duckness that is not dependent on looking exactly like a duck. Moreover, this, by the way, is how many of you are familiar with the classic Pepe Le Pew cartoons? Yeah, it's Cartoon Network stuff. So the basic plot, there's a whole bunch of these, but the basic plot is always the same. Pepe Le Pew is a French skunk. A French lover skunk. And this cat, female cat, gets a white stripe down her back by some paint or something like that. And Pepe spends the next 5 minutes of the cartoon chasing her around, trying to get her to fall in love, and she doesn't want to fall in love because she knows he's a skunk, and she knows that she's not a skunk. What's funny about this, the reason this is funny for little kids, is that little kids know that the fact that she's got a white stripe down her doesn't make her into a skunk. She's still a cat who happens to look like a skunk, and isn't that funny because the skunk is chasing around after her and getting hit in the head with bats and stuff like that. And all, it's good things that happen in cartoons. So not only do kids know that things have an essence like that, they are also, well, to be a little recursive here, they're innate nativists, it appears. They believe that these properties came with the system and were not learned. So Susan Gelman did a clever experiment where what she did was she said, see this kangaroo? This can be a kangaroo as well as a duck, I'm sure. Anyway, take this kangaroo. This is a baby kangaroo. It's a newborn kangaroo. And you know what we're going to do? We're going to take her and we're going to give her to the goats. And she's going to get raised by the goats. Okay? And now she's all grown up. Let me ask you a few questions about her. Does she have a pouch? Well, yeah, sure. That's pretty straightforward. That's not the interesting question. The interesting question is she going to be a hopper or a climber? And little kids, 2, 3-year-old kids, will say, this is going to be a climber. It's going to be a hopper, so I've got to get it right here, otherwise you'll get hopelessly confused. It's going to be a hopper. It was a kangaroo at birth. Kangaroos hop. It's part of their essence. The fact that she lived with the goats isn't going to change that. This is the amusement value of the Disney Tarzan cartoon, right? Tarzan gets raised by the gorillas. How many have you seen that? Oh man, when did that come out? It must have come. I guess all right. I got to calibrate my Disneyness here. Which Disney movies came out when you were of an age to watch them? Aladdin. Oh, you were too old when Tarzan came out. Oh, so you're the Aladdin cohort. Jungle Book came out when I was kid. Not quite. Actually, Jungle Book is the ones that came out when I was a kid were things like Sword in the Stone. I thought that was great. That was good stuff. And don't claim that I was a kid when Snow White came out. That was my father. But anyway, so in Jungle Book works, right? Jungle Book works, but Tarzan works. You get raised by the wild animals, but you're essentially a human, and that eventually catches up with you. Actually, kids are incorrect nativists because they believe things that turn out. And it's true that the kangaroo will probably hop even if it gets raised by a goat. But suppose we have here a Chinese baby, and we take this Chinese baby and we bring it to the United States, and it's raised in California. Will that when that kid grows up, will she be able to speak Chinese? Depends on the what?
In California.
In California, yes. It depends on the neighborhood. But kids aren't quite clear on these demographic issues to the same way. But a little kid will figure incorrectly that language is one of these essential properties. That if you're Chinese, that means you can speak Chinese. You might be able to speak English too. You could learn that. They can figure that out. But that you'd have a privileged ability to speak Chinese because, after all, you were a Chinese kid, and that ought to work. If you're a Chinese kid who grew up in an Anglo linguistic environment, you may have discovered that there were plenty of your relatives who also thought you should be able to speak Chinese, but that's a different issue. In any case, little kids start certainly with a notion of objectness, and probably quite early with a notion that objects have essences, and then they build on that in this little scientist kind of a way to get closer and closer to what we consider to be the adult concept of whatever, alive or kangaroo or any of those any of those sorts of things. Here's a case where the adult state is not particularly fixed, but where nevertheless what you're doing is you're elaborating on juvenile concepts, not suddenly discovering the notion that there is such a thing as a concept. Okay, I want to do egocentrism still, but I will start doing that when that thing says 310. If you can count.
What happens if you ask a kid if he's alive?
Oh yeah, kid will say it's alive.
Why?
What? Fine, he can breathe. He can do the things that he thinks alive might mean. Oh, I got to draw another picture here. That sounds more symbolic than kids. The color change to indicate that this is what's happening sounds too symbolic. I don't know if anybody's tried to find multiplication evidence in kids. Maybe what you could do. Wait.
Tumble the box.
No. I think somebody has done something like you've got a box, you put two thingies in it. Now you move in an identical box next to it. What would you expect to see? Presumably 2 times 2 is 4, or 2 plus 2 is... Anyway, I think somebody's tried that. I don't remember if it works.
But what about, it seems like, with the Pref experiment, did the kids actually take a little bit to learn that what was going on in the box didn't affect the number of things inside? Or if you did suppose you put the box down and took it away and there was only one thing there for the first trial, would the kid be surprised even at the very first trial?
I think the answer is yes, but I'm not quite sure of that. I would have.
If it wasn't, then I was thinking that it implies the kid had to learn a little bit.
No, I think the evidence. I think the evidence is that it's there to start.
Okay.
But I'd actually have to look that up. Okay. Whoops. I'm a minute later than I claimed I would be. Oh well. Let us talk about egocentrism. So, you will recall that the basic problem here was that the kid seemed unable to take the point of view of another. In this case, the mother on the other side of this table. The kid asked about things like the river and the hut, claimed that the mom could see him, even though mom couldn't see him, only the kid could see them. You can get kids to perform quite well on this task if you come from, Nebraska instead of coming from the Alps. So in one version of this experiment, so that 4-year, how does this... So I think the answer is that 4-year-olds fail this. You can get 3-year-olds to be successful in an equivalent task if what you do is just simplify the situation. So there's a version of this that may have a picture in the book still, I don't remember, of a sort of a city block with a car in it and a Sesame Street character, and you drive Grover around the block or something and ask questions about that much simpler situation. And then the kid can successfully answer questions from the vantage point of the mother, as if part of the issue here was that the task was just too complicated. Oh, I never mentioned, the M&Ms are under there somewhere. I never mentioned, well, why is it that the kids bomb the M&M task? That seems to be the case, an issue where you're asking kids who haven't gotten to the successful counting stage to do this, and they can't do it either with the numerosity or the subitizing piece, so they fail the task. If you make the M&M task, if you put that into either the numerosity range or the subitizing range, little kids will succeed in doing the task. So if you say, would you rather have this pile with 2 M&Ms or 3 M&Ms, little kids don't bomb that. They bomb, 5 versus 6 or 6 versus 8, things like that. And a similar sort of thing seems to be going on here, that the task is in some fashion a little too complicated for them. How far can we push this back? Well, if you take 2-year-olds, suppose you take 2-year-olds and you give them a pair of sunglasses. Put the sunglasses on the kid. Kid looks around for a while. Now we take the sunglasses. They may have been mirrored shades even. And anyway, put the sunglasses on mommy. And you ask, can mommy see you? Well, you can't see mommy's eyes anymore because of the glasses. But the kid, even a 2-year-old, will be able to say, yes, indeed, mommy can see me, even though I cannot see mommy's eyes. Normally, if mommy is doing this, it's a pretty good bet that mommy can't see you. And that's the root of a lot of, entertaining games. But they can manage to solve the problem if it's simplified to the point of sunglasses on or off. And this if I can see you, can you see me thing, you can see as you get more and more complicated that it takes you longer and longer to solve the more and more complicated versions of it. You don't remember what it was like to be thinking when you were a 2-year-old, but you may remember a stage later in your life when it was not clear to you how mirrors worked. That if A can see B, B can see A in a mirror. This is the sort of thing that amuses sort of early school age kids often. You can see around the corner. I can see Dad around the corner there. I bet he can't see me. And it comes as a shock that Dad can see you, because the mirror kind of works both ways. And then there are more complicated arrangements with keyholes and stuff like that, where it takes even longer to be able to take the point of view of the person on the other side. So some aspect of this is simply a matter of complexity. In fact, Paul Bloom and his student, actually I should mention, Paul Bloom is married to Karen Wynn. They were both students, both TAs for this course, and are now both professors at Yale. Anyway, Paul works on similar sorts of problems and talks about the curse of knowledge that shows up in adult behavior too. That it's very difficult, it's often very difficult to remember that somebody else doesn't know what you know. And so it's a problem for me teaching. It's the things that are hardest to teach are the things that I don't know anything about. That's not surprising. The second hardest category are things that I know too much about, because it's hard to remember how little you know about vision. How can it be that you haven't actually spent the last 18 years of your life bathed in visual phenomenology? I forget that from time. You can try using that as an excuse on the exam, but forget it. We'll still take the points off. So that turns out to be an example of the curse of knowledge. Or another example would be if you've ever been giving somebody directions while you're sitting next to them in the car, you might discover that you go past the street where they were supposed to turn because you knew you were supposed to turn there. And you just kind of forgot that they wouldn't know that, and that's why you were sitting there supposedly giving them directions. It's hard, even for adults necessarily. It's hard for adults sometimes to take the vantage point of another person. Now, one of the great examples of this in kid behavior a paradigm that's yielded an awful lot of research, which gives you some insight into this, if you like, this curse of knowledge problem, is what's known as the false belief task. The first false belief you need is that this is Big Bird from Sesame Street. All right, so here's how a typical false belief task experiment might work. Big Bird comes. You're watching this. Big Bird comes in to the scene, and he has candy, and he puts the candy in. What is this? I don't know. This is the refrigerator. He puts the candy in the refrigerator, and he goes out. Okay. Now I didn't draw. I didn't draw Grover or whatever, but Grover comes in, takes the candy out of the refrigerator, and puts it in the drawer. Okay? Now, Big Bird comes back in. He didn't see this, but you saw this. Big Bird comes back in, and you are asked, where will Big Bird look for the candy? And your answer, if you're like a 4-year-old, is that Big Bird will look in the drawer. You cannot somehow access the fact that Big Bird thinks, in his brain, that the candy's in the fridge. When you updated your knowledge about the candy, you updated his knowledge about the candy too, in some fashion. Now, there are endless versions of this experience. This is a task that 4-year-olds will fail, younger than 4 will fail, older than 4 roughly will tend to get. There are endless tasks that look at this and try to break it apart, see what's going on here, in developing this ability to take into account what is in the mind of another person, or bird, as the case may be. This is sometimes talked about as mind reading, and is sometimes described as the major problems, or the major social problem in autism. That may be one of the reasons that autistic kids and adults have a real problem relating to other people, is an inability to understand that other people have mental states, which you have that ability, but here you've failed. You as a 4-year-old have failed to manage to keep track of Big Bird's mental state. Okay, well, let's do a variation on this. So here's a variation where you don't see that initial scene. Okay? And now you are asked to guess. The candy is either here or here. Where do you think that the candy might be? Well, you say, 50-50, right? Well, I think the candy's in the drawer. Okay, now Big Bird comes in and you're told, well, Big Bird thinks it's in the fridge. Okay? Where's Big Bird going to look? And the answer now is, even if you're as young as 3, that you say Big Bird's going to look in the fridge. Your guess isn't strong enough to overwrite your understanding of what's going on in Big Bird's head. This tells you something important. This tells you immediately that you know something about the contents, that you're capable of understanding something about the contents of Big Bird's head. It's not a complete blank to you. Even younger than that, little kids can see somebody playing with a banana, pretending it's a phone, right? And you ask, does he know that it's not a phone? And yeah. The 2-year-old will tell you, he's just pretending. And you can have the notion that somebody else could pretend to pretend something. So again, you can push this notion of being able to read minds back earlier if it gets simpler. And maybe this isn't really about the contents of Big Bird's mind at all. Here's a cute version of the experiment done by Debbie Zajcek once upon a time. Big Bird comes in. It's the original false memory game, false belief game. Big Bird comes in, puts the candy in the fridge. But this time, Big Bird takes out his camera and he photographs it. So he's got a picture of it. There's the candy in the fridge. Okay? Now, Big Bird goes out. And Grover comes in, moves the candy to the drawer. You now know that the candy is in the drawer. Big Bird comes in. You are asked, where's Big Bird going to look for the candy? Even though Big Bird has taken a picture of it, even though there's now a physical instantiation of the contents of Big Bird's mind, you still say it's in the drawer. You, as a 4-year-old, are still unable to keep track of this. This suggests that maybe the problem is less with your ability to see into somebody else's mind and more with something like the capacity of your working memory. So if you think about it, this is very parallel to a Loftus experiment I talked about either last time or the time before. You see somebody go through a yield sign. You later hear that it was a stop sign. And you believe, you come to have a false memory, or a false belief if you like, that it really was a stop sign. Because we've managed to somehow overwrite your memory here. Maybe in this case what you're dealing with is not the development, a qualitative change where you're seeing a change in the ability to see into somebody else's mind, but a big enough working memory that you can keep track of the task. So another case where the development here waits on the development of another ability, a separate ability, in this case working memory. Okay, that's as good a place to stop as any, so I'll stop.